Okay, so I'll try to show you how you can play at the supramolecular level with graphene in order to create some complex structure and hopefully that are functional. And so I don't spend any time into trying to convince you why it is worth to spend our effort on graphene. There are, thanks to the fantastic physical chemical properties that it holds, one can expect and hope a number of technological applications. Now, these are the questions that I posed out myself, essentially in 2007, when we decided to start to play with graphene. That is how, as a chemist, can we contribute to graphene. There are a lot of physicists around, and so I thought that these were the things we could actually contribute with. That is combining, of course, chemistry, graphene with molecule in order to gain something in terms of processing, in terms of tuning physical-chemical properties, and eventually endowing new properties to graphene in order to create some multifunctional, therefore multi-responsive graphene-based materials. And so this is going to be the highlight of my presentation today. I will give you a few snapshots of essentially a few things we have been doing in my lab. So I will start with playing with graphene oxide. Graphene oxide actually is the easiest way as a chemist to play with graphene because actually can be easily produced. Start from graphite powder, you do some oxidation cycle like Hammer's method, you create this graphene oxide. They are fantastic in the sense that you solve all problems related to solubility. You have a lot of different functional groups that you can use to do functionalization of the covalent and non-covalent level. Of course, the physicists do not agree with this because most of the exceptional properties of graphene are lost. But nevertheless, you can do a lot of different chemistry. And so what I'm going to show you is not application in electronics, where graphene oxide is not the right building block, but rather application in energy. And so this was a work of an excellent postdoc, Xiaoyan Zhang, that joined my group in 2014. And so the idea here was to try to use graphene and to build up some highly robust porous architectures with high surface area for energy applications. And the idea is we wanted to grow from a two-dimensional object, we want to grow a three-dimensional architecture in a kind of layer-by-layer approach. And if you want to grow, let's say, vertically to the basal plane of the graphene, you have to do a chemistry where you put your pillars that are actually interacting with the only functional groups that are on the basal plane, and these are the epoxide group. And so the chemistry we have performed is a pretty simple one that is already known, ring opening reaction with amino-functionalized unit. Let's say the novelty of our approach compared to what you can find already in literature before is that we decide to play with a building block that is benzidine, which is known to undergo oligomerization or polymerization if exposed to mild temperature. So you can see that when we combine the graphene oxide with benzene at room temperature, we form essentially a layer-by-layer structure with a single benzene that is connecting a distant layer of graphene oxide. If you do this at 45 degrees, the cartoon is such that you have a dimer of the benzene, and at higher temperature, like 80 degrees, you have an oligomeric form. And actually, this kind of growth is a way to tune the distance between this and layer, the average distance between this and layer of graphene oxide, which is well reflected by the X-ray diffraction data that have been recorded. You can see that gradually we increase the average distance between the layers. Now, this, of course, is reflected also in increase of the porosity, and so the surface area is increasing, in particular going from GO to room temperature to 45 degrees. It does not further increase when we increase further the temperature, and the reason is very simple that you can see here that due to the finite persistent length, the benzidine oligomers start adopt not a vertical, let's say, configuration, but rather a bent one, and so the area, the surface area does not increase linearly. Now, nevertheless, we have been trying to test this kind of architecture as electrode for supercapacitors. And now here, of course, we take advantage of specific surface area, and we do a bit of hydrogen reduction in order to gain some electrical conductivity. Otherwise, our system would be completely insulating. And the presence of the use of benzene allowed us to have a certain amount of nitrogen doping in our system. And the result were quite positive in the sense that we can get some specific capacitance that is, in all the three cases, higher than one of the standard graphene polyaniline nanocomposite. Now, that is just an example how you can make it functional. You can grow a three-dimensional structure out of graphene. Now, the question is, graphene oxide, as I said, is easy to functionalize. Is that the only system you can do this game at the three-dimensional level? The answer is no. You can do a lot of chemistry based on 2D materials. You have a broad choice of the materials you can think of. And here are just, if you think about covalent chemistry, of course, the ring opening reaction is what you can use with GO. With graphene, the yield is a bit lower, actually, to be honest, but you can do the chemistry based on diazion salts. And for example, if you play with molybdenum disulfide here, you can do a lot of thiol chemistry. And this is what I'm going to show you now. I will show you later how non-covalent functionalization can also be exploited. So this is just a very recent work that we have published. And the idea is very simple, that you start from molybdenum disulfide. You can buy the CVD, or you can have a Scotch tape, and there are a certain number of sulfur vacancies. And now, this number of sulfur vacancies, it can be used in order to attach thiolated molecule to this. Now, you might be unhappy with the number of sulfur vacancies that you have, and so the question is, can you increase them? And the answer is, of course, yes. So the approach is very simple. You use an argon beam, okay? And the argon beam, you increase quite drastically the number of defects, and this is what is reflected in the electrical characteristic. You can see that starting from the pristine, you can increase the amount of sulfur vacancies that are missing. So this is 1% of sulfurs are missing. You can go up to essentially 35%, and then you don't measure any more current. But you can, if you want, you continue your irradiation. You can essentially create a pure molybdenum type of surface. And then the question is, you create all defects, and can you make use of it? Of course, yes. So the idea that we played here was a very simple molecule like butanediol, and we use this in order to fill these defects. And so to essentially, we start from the IV characteristics in our field effect transistor backgated, that you have the pristine device here. When you, after 2% of sulfur vacancy, you can see that the IV characteristics are much more modest. You can gain it back by functionalization with thiol chemistry. So with butanediol. Now, why is all this interesting? It's interesting because essentially it's a super easy way in order to functionalize molybdenum disulfide. And so you can attach any kind of function you want, okay? You can do the same game also with other type of disulfide dialkylcogenides. Now I'm going to pass to the next topic, that is how you can produce graphene. And we'll focus on a mild way that, let's say, you can do in any chemistry lab. And in fact, there are a number of different approaches you can use to fabricate graphene. You can have the Scotch tape, you can have the CVD, more physical or slow type of process. And we focus our attention actually on the most mild approach. That's the one of liquid phase exfoliation. That somehow reflects a bit what was presented this morning already by Alan. Now the idea is very simple here. You start from graphite powder, you put this in a given solvent, and you do a cycle of sonication and centrifugation. Sonicate to exfoliate, and centrifugation in order to purify. Now, you have to choose the right solvent. Usually this is NMP. And eventually, it is said in literature that you can use surfactant that can be used as stabilizing agents. Okay, so the surfactant can be this red bar. These are organic molecules. Now, the question as a chemist is what is the best organic molecule you can use? And so, usually in the community, this kind of approach has been pioneered by Johnny Coleman and Andrea Ferrari, that they are physicists, and so they are less creative, or let's say more narrow in their choice of chemical system. The chemical system we decided to play with is a very banal, so are purely alkanes. And the reason why I chose to go for alkanes was because I was thinking about the work that my PhD advisor, Jürgen Rabe, published in 1991. This was the first work on solid-liquid interface study by scanning and microscopy of alkanes on graphite. And so it showed that whatever end group the linear alkane can have, like methyl, carboxylic, amino, or OH group, they form lamella. These lamella structure are highly ordered, and this is an evidence that there is a very strong affinity through van der Waals interaction between alkanes and graphene or graphite. And so this is what I thought. We use a long alkyl chain that has high absorption energy for the basal plane of graphite. It is soluble in organic solvent. This is interesting for us because one of the applications we have in mind is electronics. And well, actually, we find out that from the solvent mixture, we can separate the alkanes from the graphene just by exposing this to 70 degrees, okay? And so we take advantage of the alkanes in order to promote the exfoliation, but then we get rid of them. You can use different type of alkanes. We focus our attention on C8 and arachidic acid C19. Of course, the energy of absorption of graphene should be higher than the one of the solvent, that is NMP, otherwise it makes no sense to use the alkanes. Now, this is, for example, an example of the arachidic acid for nice lamella on the basal plane of graphite, and the same result we have on CVD graphene as well by STM. Now, just a snapshot to show that you can quantify the yield of exfoliation, so the amount of graphene you can bring in solution. And you can see that if you compare the exfoliation of graphene in pure NMP with the one obtained with phenoloctane or arachidic acid, there is a gradual increase of the exfoliation yield up to 50% when you use arachidic acid compared to the pure exfoliation NMP. And so this is due to the role of the van der Waals interaction between molecules absorbing on the basal plane of the graphene and stabilizing the graphene phase once exfoliated. Of course, you have to do your characterization. We did Raman that showed no more evidence of AB stack of the, let's say, graphitic-like structures. That was done by Cinzia Casiraghi in Manchester. We have the electron microscopy high resolution that was done by Ovidiu, and it showed that mostly we have mono, bi, and tri layers in our sample, no matter which one of the three different types of sample we are dealing with. You always like also to see how your sample looks like, and so by SEM, by comparing the bright to the dark field, we can see there is a single flake here with a size of about 30 micrometer, and actually the comparison of the contrast in bright and dark field suggests that this is a single layer thick flake processed from solution NMP. Now, going back one step, you can do exfoliation also without molecule. You can just do this with a given solvent. You can use NMP or another good solvent for doing the exfoliation by sonication is dichlorobenzene or dichlorobenzene. Now, we found out something that was unexpected, that you can play with the power of your sonicator, your bus sonicator, when you play with NMP in black, and there is no major change when it goes from 600 to 1000 watt. And whereas we found a major change when we were increasing the power of sonication going from 600 to 1000 watt using dichlorobenzene. And the reason for this is actually that it is known that when you deal with aromatic molecules that are chlorinated in the presence of ultrasounds, they can generate some radical speeds that are highly reactive. And actually, this was the reason why we obtained some different type of graphene. When we look more closely to this kind of graphene produced here, you can see already that the color is drastically different. While the average size of this kind of graphene here is on the order of 200-300 nanometers, in lateral size here, the average size is about 17 nanometers, and they are fluorescent, okay? So I will skip all the characterization of the physical properties, but this is just a simple way to create, let's say, graphene nanodots. So watch out about what solvent you use when you do sonication. Let's go back to molecule, and so you can do, as I showed you, you can use alkanes to do exfoliation promote the exfoliation and stabilization of graphene in organic solvent. Now the chemistry of alkanes is very, very simple. You can think about at the end of the chains to put whatever function. And so we decided to focus on photochromic molecule as a head group to put at the end of the aliphatic chains, which photochromic molecules are smaller molecules that are able to undergo efficient and reversible photochemical isomerization between two states that has completely different properties. And so the two most famous photochromic molecules are the azobenzene and the diaryletin. The azobenzene, you can switch from the more linear transform with UV light into the more compact, so bulky cis form, and you can go back either thermally or with visible light. And so the idea is to photo-switch a molecular entity, to use a photo-switching molecular entity as a gate, and so translate an information that is a light information into a change of the electrical properties of the material. Now, why did we decide to focus on the alkyl substituted azobenzene? And the reason is because we published a paper in 2009 that was not at all on graphene, was just a simple paper work done together with Davide Bonifazi about this kind of molecule, how they were self-assembling on the basal plane of graphite, and looked by STM their isomerization in situ at the solid interface. And so what we noticed is that essentially when the molecule was in the transform, it was forming very nice lamellar structures. While we were radiating with UV light, what happened is the molecule were desorbing out of the surface of graphite. And so this meaning that the cis has a very lower energy of absorption for the basal plane of graphite compared to the trans. We turn off the UV light, the cis state is metastable, and so gradually the monolayer of the trans molecule was reformed spontaneously. And so anyway, the piece of information we learned out of this study is that we can play with the azobenzene, alkyl substitute azobenzene, because in the two states there's different type of energy of absorption on basal plane of graphite or graphene. And so my idea was very simple: long aliphatic chains to promote the intercalation of the azobenzene between layers of graphene during the exfoliation, and then at that point we can play with isomerization. So in other words, I can do cycle of UV and visible light in order to change the shape of the molecule, and so to have it more flat, and so to have a closer packing between a distant layer of graphene, or irradiating with UV light in order to have a spring, this kind of spring that increases the distance between the adjacent layer of graphene. Now, of course, if this is the case, when you irradiate with UV light, you should decrease the yield of exfoliation because you promote the distortion, or you weaken the adhesion between adjacent layer of graphene. And that actually was the case that you can see. You can play with temperature, but I will not go into that detail. You can just focus here. You can see that you have the yield of exfoliation that is increased while you irradiate your sample with UV light, your solution with UV light. So this is bicomponent solution of graphene plus isobenz that is integrated between a distant layer of graphene. Now, of course, again, you have to do all the characterization. Raman, in this case, was done by Andrea Ferrari in Cambridge. Electron microscopy was done by Vittorio Morandi. Again, you have mono, bi, tri, and a bit of tetra layer. And now my idea was to use this kind of bicomponent ink to create some photo-switchable electrical devices. And so the idea is that we took this ink, we deposit this in between two interdistated electrodes of a transistor, and then you can in situ do irradiation either with UV or with visible light, and you can see that actually there is a nice response of the current through the junction due to the irradiation different wavelengths. If you do the same game with azobenzene ink deposit between the same electrodes, but in this case, where the graphene ink that has been produced in absence of azobenzene, so in pure NMP, there is not at all a response to the light stimulus. So the presence of the azobenzene plays a role in order to change the current with a photochemical stimuli. Now, why this happens? It happens because both modeling and X-ray diffraction showed us that the average distance between the DSN layer is increasing, going from the trans to the cis. Okay? And so it's just the probability of the charge to hop from one to the DSN layer. Now, you have to bear in mind that this, we played, I showed you very nice images on the formation of lamella of alkanes on the basal plane of graphene or graphite, but actually this was not really the case when we were doing sonication. So in situ during the sonication, you have to expect the molecule are quite disordered. But can we try to gain a higher degree of order of molecule on graphene and use this in order to confer some new properties to the graphene-based materials? Now here, we thought about playing with heterostructures. And so the heterostructure you can think about what we did not have for lunch. You can think about having a hamburger and add the cheese. And if you eat them separately, the taste would taste different than eating them together, okay? And then, of course, you can think that you can also create some tastes that are much more artificial and much more complex if you build up a layer-by-layer structure like this. So this is a work, actually, of Marco Gobbi, the physicist, Sara Bonacchi, she is a chemist, and Emanuele Orgiu, that is engineer. So I think this kind of work really needs an interdisciplinary team like that. Now, this picture was kind of already introduced this morning. The 2D heterostructure. The idea is to use different type of layers or different type of 2D materials, and you can use this to create some, let's say, 2D periodic potential, in particular I'm playing with the monoarray patterns, okay? So these periodic potential are quite interesting, but there is no way to create 1D periodic potential. So the question is, here the interaction between the different 2D systems are van der Waals, and it's just mechanical superposition of one layer on top of the other. Can we do the same just by using one type of 2D materials and putting molecules on the top? And so that is a kind of the game. That is, instead of this physics approach, to use a chemistry approach. And people have been putting different type of molecule that can be electron donating, electron withdrawing on the basal plane of graphene. Without looking too much into the order of the molecule on the basal plane of graphene, you can, well, here's a different example. I will not go into them. Now, what we decide to play with is a molecule that, again, has a very long alkyl chains, because the long alkyl chains for us was a motif in order to create some orders, supramolecular structures, so supramolecular lattices on the basal plane of graphene. And then, actually, we start from this diastereene molecule. And this diastereene molecule radiated with UV light, it formed carbines, and in the presence of a chlorinated solvent like chloroform, actually, this creates some products. And the most popular product in our mixture is this one here, okay? And so you can see also photochemically that there is this kind of peak that is associated to the reactant that is reduced by formation of the product. Now, the idea here was very simple. It's an ex situ experiment. We start with either the diasterene or the diasterene that is irradiating the beaker, so our product. We self-assemble them on the basal plane of graphene, dry film by spin coating. And then actually we obtain this kind of order of some functional group. And these are the functional groups. And you can see already by STM that we have some nice lamellar structure. zoom in, and this is a zoom out on graphite. So the area is about 300 by 300 nanometers square. And you can have the same type of lamellar structure also on CVD graphene on silicon dioxide. Here, the surface is a bit more rough, so the images are less nice. I want to stress that the molecules are quite similar, so identical unit cell, and the film were dry, okay? So what we have created here essentially is 1D geometry, and we obtain some periodicity in our structure. And now at this point, we can make a real device. We can look at the IV characteristic of our monolayer CVD graphene. So we start from this curve here. There's a curve in black. And you can see that we have a neutrality point that is located at 0. When we absorb the diazoline molecule, there is a minor shift, so a minor doping, a minor shift of the neutrality point here in red. And actually, there is a subtle increase of mobility. You can notice here. When we do the same experiment, but this was done on MB2, you can see that there is a large shift of the neutrality point up to 25 volt, and there is a huge decrease in mobility. So this is a major doping effect. And now, so in what we are doing here, we are changing let's say the amplitude of our potential. And now, why is this? So this was the help we got from Mons doing modeling. Essentially, the major difference that you have in the two systems, MB1 and MB2, is this CF3 groups that, in the case of diazoline, is pointing parallel to the basal plane of the graphene. And therefore, what you have is a small net dipole moment perpendicular to the surface, whereas in the case of the product, this group is pointing up to the surface, so there's a large net dipole moment that is perpendicular to the surface. And so we have a subtle change in packing, but a huge change in local electrostatics, and this generates a p-doping effect. Now, so this kind of p-doping effect can be really used in order to create some one-dimensional periodic potential. Now, a bit more modeling done in Mons revealed that there is a minor role played by charge transfer, but there is a major role played by the molecular dipoles that are exerting a local gating effect. And so, essentially, what the other piece of information that I have no time to show you today is that if instead of doing this photolysis in the presence of a chlorinated solvent like chloroform, you do this with an amino solvent like diethylamine, you have N-doping, okay? And so, based on the type of solvent you have and the reactivity of carbon, you can have different type of doping, and so formation of one-dimensional periodic potential with periodicity, amplitude, and sign. And so that, I think, is a way to confirm some multifunctional nature to graphene. So I will skip, I think, how much time is it left? 5 minutes? 6? Oh, okay, so I can go to the wedding of graphene with organic electronics. I come originally from the community of organic electronics, so it was good for me to try to combine the two words, and I will use this in order to improve the transistor's characteristics. And so the idea is how can you blend organic semiconductor with graphene? You can exploit graphene as transparent electrodes. I have no time to show you this. I would suggest you to do this in hybrid structure. For example, you can combine metals with 2D materials. That's an easy way to get electrodes with performance similar to ITO, both in terms of transparencies and in terms of sheet resistance. The other way is to mix graphene with organic semiconductor in order to improve the properties of the organic semiconductor and eventually confer them some new properties. And so the idea was something that we tried here and published in 2014, was one that by blending we could leverage the ambipolar transport in a polymeric field effect transistor of a given organic molecule that was otherwise purely a p-type. And now, the blending is nice, but has some downsides. The downsides are that you have phase segregation between different components. You can have random aggregation of graphene here and there. You have full control over the graphene deposition, and you have a loss of crystallinity in the semiconducting matrix that actually this would be a pain in terms of charge carrier mobility within the device. So this was the work of PhD of Thomas Moschatti. Now, what we also realized is the fact that the liquid phase foliated graphene from NMP does not hold all the electrical properties that are fantastic and are usually associated to graphene. In other words, the NMP, when you deal with NMP exfoliated graphene and you deposit this between two electrodes of a transistor, you have mobility around 1. Okay, so this is very, very low. Now, to gain a bit in terms of mobility, what you have to do, you have to get rid of NMP. And to get rid of NMP is not easy. You have to anneal your sample to 400 degrees. And so you can see already how the current changes drastically when you need a sample to 400 degrees. But if you have a blend, if you have molecules here and there, I don't think they like to be exposed to 400 degrees. And so we have to find a trick in order to combine these two components without essentially exposing the molecule to 400 degrees. And the idea was simple, to do a multi-step deposition. First, we start from silicon dioxide, and we deposit graphene patches on silicon dioxide. They want to exfoliate from NMP. At this point, we can expose the sample to 400 degrees. This is not a big issue because both silicon dioxide and graphene have no problem to be exposed to such temperature. Then we do HMDS functionalization, so we functionalize the silicon dioxide with some alkyl chain standard in order to render it some more hydrophobic, and then we can deposit by spin coating a given semiconducting polymer. And then we can put the top electrodes in order to fabricate the transistor. So these are the source and drain electrodes. Now, depending on the concentration of the solution of the graphene that you deposit, you can have different type of, let's say, coverage of the silicon dioxide surface. You can go from no graphene surface of purely silicon dioxide to more and more, let's say, densely packed surface with patches of graphene. Actually, or you change the concentration, you change the volume, it doesn't matter. The polymer we decide to play with is the following. These are both commercial polymers, N-type and P-type. Now, the more you increase the graphene coverage on the surface, of course, then the more charges pass through the graphene flakes, and so you have an increase in the mobility, both in N mobility when you play with N-type polymer, or P-type mobility when you play with a P-type polymer. And now the major problem is that the ion-off ratio is still not terrific. We will see more precisely in a few slides why. Now, if you look at the energetic of your system, these are the Ohm and Lume of the polymers. Okay, so this is the N-type, this is the P-type. They're very similar energetics. The ionization energy of the graphene that is circulating in nitrogen atmosphere lies about around 4.9. Surprisingly, when we do this kind of annealing of 400 degrees in air instead of doing this in the nitrogen atmosphere, the ionization energy goes down to 5.7. XPS did not show us any difference between these two different samples. Okay, so chemically, I'm not able to tell you what is the difference, but I can tell you that this is highly reproducible. Now, what is the situation? The situation that here we have a level of the graphene that is within the band gap. So if the level of graphene within the band gap, it acts as a trap for the charges of the semiconducting polymer. Whereas in this case, when the level is out of the band gap, the interaction between the graphene and the organic semiconductor are pure electrostatic. So essentially, the graphene can get charged with the gate voltage. And so we can use this in order to create increase the number of charges in the channel. And so here we have some traps, here we don't have traps, and so this obviously is reflected by the fact that here we measure some nanoamp current, and here we have no trap, we measure some microamp currents. You can, as I said, decide how much is extended your graphene coverage on the basal plane of silicon dioxide, and so you can have a shift from a semiconducting behavior where you have very few graphene patches on the surface, and with the increasing amount of graphene, you go to improve semiconducting behavior. Here you can follow a bit the key performance indicator, ion-off ratio, and the mobility, of course, increase with the amount of graphene on the surface, but you increasing that, you always pay a price in terms of semiconducting nature. And so you can see going to you up to a graphenic behavior where the device doesn't turn off anymore. Now, what happened is that we realized that indeed, by applying voltage to the gate electrode, we are doing nothing else than charging and discharging our graphene patches. And so you can see that we can write the information with applying a negative voltage to the gate electrode and erase by putting a positive voltage to the gate electrode. Likewise, you can do with different type of organic semiconductor, P and N type. So you can sweep essentially the threshold voltage in this way just by applying voltage to the gate electrode. And so this is nothing else than a floating gate memory. And you can make over 50 cycles and with very little fatigue. And so this, just to close up, what can we do as a chemist in the future with graphene? I think we can still have some room to improve in terms of processing, in terms of tuning the properties, and I like to go more and more towards making graphene multifunctional and other 2D materials as well, and hopefully this will open some new technologies. I need to acknowledge the number of people that were essential for this work. Xilian Feng synthesized the diaethylene together with Klaus Mullen, calculation from Mons, electron microscopy, already mentioned Ovidio and Vittorio, Raman by Cinzia and Andrea, the quantum dots, the Francesco did the Raman, and Franco did the photophysics, and the X-ray diffraction was done by Fabiola. This work has been sponsored by French money here, first row, and by European money underneath. And as I said, this activity, you need to be interdisciplinary to do this kind of research that spans from really the fundamental chemistry to real device application. And you can see here stands for engineer and C for chemist. And so I have a very international and very interdisciplinary team. And I think I'm very lucky to have such a fantastic group of people that indeed, if you want to have a working device, you need an engineer. But if you want to play with self-assembly and with molecules, the engineers are not as skilled as chemists. Thank you very much for your attention.